In this video, we are going to look at what is a transfer function. In our previous video, we talked about a mathematical modeling. And why do we need a mathematical model? And we said that a mathematical model help us to predict the system behavior without physically testing the system. And secondly, we said that a mathematical model is very important for us because we have to design the controller such as PI controller, PID controller, proportional controller, and different type of controller. Example, PID, we have the feedback system, and so on. So mathematical model help us to develop the idea such that if we want to perform a simulation of a system performance before we can actually build the system. And also mathematical model help us to optimize the system parameters. And we said many times those parameters are important for stability purpose and efficiency of a system. So we can see that we have a mathematical model and we have a physical system. And mathematical model is the opposite of a physical system. Before we build a physical system such as a washing machine. A washing machine is a physical system that we use, and before building the washing machine itself, we have to design the model of the washing machine. And we know the two approaches that we discussed in our previous video. The first one is nothing but the differential equation. And the second one is the transfer function. The important thing to differentiate between what is a differential equation and a transfer function is that if we want to model a system using a differential equation, we are dealing with the variable which is in the time domain. And when you talk about the transfer function, it is in the frequency domain, or we normally call it the S domain. And in our discussion today, we are going to look at the transfer function and why is it different from a differential equation. In control system, differential equation and transfer function plays an important role in a mathematical modeling of a system. If we can analyze the mathematical model based on the system behavior, the design controller, the simulation of the performance, and the stability and efficiency of the system, if the mathematical model is correct, now we can proceed on to building a physical system. Because in a mathematical model, we are not actually building the system, but it helps us to predict the behavior of the system without physically testing the system. So if you have a mathematical model that is correct, and when you build a system and you apply a test to a physical system, the test result must correspond to the mathematical model. And we can now define what is a transfer function. The transfer function is defined as a mathematical representation of the relationship between the input and the output of a system. We always draw a simplified block diagram of the system having the input and the output. When we talk about the relationship, if we apply some input to a system, what will happen to the output of the system? In a mathematical modeling, if we have a physical system such as the washing machine, we will now have to measure the output, which is a function of, for example, the motor. When we apply the input for washing a clothes for a certain amount of time, that means the output must work according to the instruction that is passed as an input. And to measure the output corresponding to the input, we will measure the actual happenings from the output and we compare it with the input. Input can be a reference, can be a signal input, can be a form of voltage, and the output of the system is actually the happenings that is done based on the type of system. And the input is the desired property or a reference that is corresponding to this output. So they will have a relationship. Example for the washing machine. If we turn the knob which act as a control input to a washing machine, we want the washing machine to wash for 10 minutes. And we can monitor the output of this washing machine. And if it operates within 10 minutes, now we can see that there is a relationship between the output and the input. Example, if the input is 10 minutes and when we measure the output, it takes 20 minutes for the washing machine to perform the washing, then we can see that this type of system is not stable because the input says 10 minutes while the output is taking up 20 minutes. By then, we can provide some form of relationship. And with the mathematical modeling, we can apply a transfer function to test the system without actually measuring the working of the system, such as the washing machine. So we normally provide a mathematical model such as a transfer function. And we can say if 10 minutes is the desired input and the output performance is 10 minutes, we can say that this type of system is a stable system. That means it has high efficiency as well. And with the performance of 10 minutes as an input, as a criteria, and the output it takes 20 minutes, we can simply say this system is unstable. When we compare a transfer function, we can easily, using some rule, to find out whether a system can be a stable system or a unstable system by using the model such as in the frequency domain. And most of this case is in terms of the Laplace transform. And with the key terms such as mathematical, we'll derive most of the maths based on the Laplace transform. And this transfer function is widely used in control system. If you want to really understand what is a control system, by now you should be able to know what is a transfer function. And when we talk about the signal processing, there is transfer function involved in determining the signal as an input and output of a system. And also, if you are to learn electronics, you have to know what is a transfer function because it is the relationship between the input and the output of the system. And we know that by analyzing the circuit, it will be in the frequency domain, unlike in the differential equation where we analyze the system in the time domain. Therefore, the transfer function notation can be we can say the transfer function g of s, where s represent the S domain, which is the frequency domain analysis. And now we can say that G of S as a notation is equals to the output of S over the input of S. And this is our basic transfer function where we have the ratio of the output versus the input. And remember that the output, the analysis is in the Laplace transform as same as the input. To make a small comparison, we all are familiar with the time. So the time is the variable that we want to consider under a time domain. In a transfer function, what we are interested in as a variable is the frequency of the system. And any measurement will be taken with regards to a frequency. Unlike the differential equation where most of the analysis is based with respect to the time. And some of the key concepts about a transfer function we should know from the equation is they have what is called a polynomial. And we can see that the output is called a numerator polynomials, and this is the denominator polynomials. And it is important for you to understand with both the numerator and the denominator, there are roots of the system. This root of the system determine a crucial component in determining the stability of a system. The numerator, the roots, is called the poles, and the denominator is called the zeros. The roots of the denominator, which is called the poles, it determines the stability of the system. And on the other end, the roots of numerator, which is called the zeros, these now affect the system response. When we talk about the response, we are talking about nothing but the output of a system. So the zeros affect the output of the system, while the poles, which is the roots of the denominator, it determines whether the system is stable or unstable. And because we have two types of main system under consideration, such as the open loop system and the closed loop system. And we can now be able to apply a transfer function to both of these systems. By analyzing this system, we can start by looking at what is the open loop system. We say in our previous video about the open loop, we can show it in terms of the block diagram, where we have the input to the controller and to the plant and the output. When we talk about the input, since input is a signal having a quantity, and this quantity can represent either in the time domain or the frequency domain. However, when using a transfer function, we normally represent all of them using a frequency domain. And if we say the input is x of s, which is a signal representation of the desired signal from the input, which is represented in the s domain. And we can have the controller as c of s, and for the plant we can say p of s, and the output we can say y of s. Because a controller is a system having parameters that may influence the input, it now can be represented as the C of S. And remember that if we are to analyze the controller, we can have point B and point A. And now we can say C of S is equals to point B of S over A of S. A of S is nothing but the input signal, and the B of S, which is now the output of point B. So if we want to find B of S, which now represent the numerator or the output of the system, will be equals to C of S dot A of S. And simply, the signal output of B of S is equals to C of S dot X of S, because there are no other block diagram in between. So from this we can see that X of S is equals to A of S. Such analysis can be more helpful if you want to analyze a system. So we can see that A of S is nothing but X of S. Now let's look at point C. From here we can say that point C of S, where it is a signal output of the plant and it is represented in a frequency domain, is simply equals to y of s. Therefore, if we want to find the transfer function of the plant, the transfer function is simply p of s is equals to c of s over b of s. And from here we can see that if we want to find the output, which is the numerator of the plant, we can have C of S is equals to P of S dot B of S. And we can simply say B of S is now the output of the controller or the response of the controller, and the C of S is the output of the plant or the response of the plant. Because in our previous discussion, we say that open loop is easy to analyze and it is easy to implement when stability is not that important. We have discussed some system where we don't need stability, such as the washing machine. That means we implement using a open loop, and such mathematical model will become important. Now let us see how we can analyze this by using our derive equation of the S-domain representation. Now we can say that the transfer function of this system G of S is equals to the output of the system, which is the Y of S, divided by the X of S, which is the ratio of the output and the input. And if you look closely, the G of S is nothing but a combination of the controller and the plant itself. We say the system is the output over the input. To simply analyze this, we can say the input is equals to the G of S, and we have the output. And we can break it down by saying X of S is now the G of S and is now the Y of S. All these are a same representation of the system. If we now want to find the overall, then we can simply say that G of S is equals to, when we look at the Y of S, because in a system like this, we can easily find that the g of s is equals to y of s over x of s, and the response, which is now y of s, is equals to g of s x of s. It is very important to know that the g of s is the transfer function and the y of s is the response of the system. If you are given a question to find transfer function and another question to find the response of the system, now you can only transpose this equation to find the response by looking at the output. And we multiply x of s with the g of s to gives us the y of s. So with this idea in mind, we can say that y of s is equals to x of s dot c of s dot p of s. This is now the response of our system. So it is now equivalent to y of s over x of s, which is also equals to c of s dot p of s. If you check our previous video, we have some operation that we look at addition of a signal, multiplication of a signal. When the blocks are connected together like this, we mostly multiply. So the output will be equals to the plant, the transfer function of the plant multiplied by the transfer function of the controller times the input to get the output response. And this g of s can now be seen as the overall transfer function of this system. In most control system design, you will be given a notation such as c of s and the p of s, and they represent the transfer function of the plant and the controller or any other physical system that is connected to form the overall system. So I will give you some few examples with that regards, so you can be able to appreciate how we can calculate the open loop. And open loop is nothing but it is quite simple to analyze. And remember that this is only the block diagram representation. Later on, we'll look deep into applying a Laplace transform into each of these block diagram so we can solve for the response of a system. Maybe example 1, we can say x of s as an input to m of s, which is a system, and we have y of s. So m of s is now the transfer function between the output and the input. So m of s is now equals to y of s over x of s, and this is the transfer function. And we can have y of s is now equals to m of s times the x of s. Now what is this? This is now our response of a system. And the example 2, now we can say x of s is equals to m of s to n of s, and we have y of s. So it is simply, we can say these two is now equals to g of s. So we can say g of s is equals to m of s dot n of s, which is now equals to y of s over x of s, which is now the transfer function. And thirdly, if we have x of s to m of s to n of s to o of s, and we have the y of s. If we simply group this one into g of s, Now the equation will become g of s is equals to m of s dot n of s dot o of s, which is equals to y of s over x of s. Also for this one, I forgot to tell you the response. So the response is just simple, is y of s is equals to g of s dot x of s, which is equals to m of s dot n of s dot x of s. So this now is the response of the system. So similarly, in this case, we can see that this is the transfer function and the response is y of s is equals to g of s dot x of s, or it can be broken down into m of s dot n of s dot o of s dot x of s. So this is the response of the system. So from this one, we can easily analyze if we want to find the response of the system. And since it is connected in a linear manner, we multiply all of this to get the response, similar as what we have discussed in the previous diagram. Since the open loop is a series of a component arranged in a sequential manner, that means there are smaller devices or a system that makes up the overall system, we can say x of s can be equals to 1, we can say it is equals to 2, it is equals to 3, it is equals to 4, and we can say it is equals to the nth system and having y of s. So 1, 2, 3, 4, 5, they all represent a smaller system or a subsystem within the entire system, and we can simply analyze the response by multiplying backwards. That means all the gain of each of the system must be multiplied with the input to get the final response. And we can multiply the system gain 1, system gain 2, system gain 3, system gain 4, and all the way to system gain n. And by analyzing those gain, we now multiply with the input to produce the response. So by looking at this, we can see that those smaller subsystems such as 1, 2, 3, and 4 in an open loop system plays an important role, which is more simplified than the closed loop. So this block diagram can be simplified into x of s, which is equals to the overall system and which produce the response, which is y of s, and it is that simple. This is the early step to understand the transfer function in an open loop system, because it is important when you want to learn control system, signal processing, electronics. It becomes more handy to learn the mathematical modeling